so far. All right, I'm going to get started since it is 12:30. And I'm just going to be going through test 4. Is anybody having trouble hearing me?
Nope.
No.
Okay. All right, so we're going to just go through each of these questions, and I'll be sort of just telling you what kinds of questions we're dealing with and then pointing to where those are in the notes. We also have videos for everything that I talk about here as well. And I'm hoping that you've watched the videos, because I think that they're probably one of the more useful ways of being able to get an idea of how these things react. I'm going to actually mute you all, but if you need to talk, just go ahead and unmute, and then you can ask a question. Okay, so we'll start off with question 1 here. This kind of question that we're looking at here at the top is called it's a Claisen condensation. Specifically, it's a regular Claisen condensation. There's 2 flavors of Claisen condensations that we talk about. Now, you'll notice also that there's no number out the front here. You might be expecting to see a number 2 or something like that there, because it does require 2 equivalents of the same thing. But I want you to understand that if you're dealing with a reaction where you've just got one thing at the front here, and you know it's a Claisen condensation, that you'll need 2 of these to react, because if you've got a bottle of this, you just don't have one molecule. You can't just have one molecule of anything. There's always going to be a lot more of them around. So that's why it's not necessary to have the 2 here. Now, just to give you an idea of the kind of reaction we're talking about here, let's see if I can get there. Here we go, ester addition reactions. So this is the Claisen condensation that I'm talking about here. And that's distinct from a crossed Claisen condensation, because a crossed Claisen condensation involves 2 esters, but they're going to be different. And one of them doesn't have an alpha hydrogen on it. Now, when I have the terminology, when I use the terminology alpha hydrogen, what I'm talking about here is the hydrogen that is on the carbon directly next to the C double bond O. That's going to be necessary to remove first in the first step of the reaction here. I'm going to stop for a second here. Does anybody have any general questions about Claisen condensation? Okay, so you can see here that in the crossed Claisen, this second one here that it's reacting with doesn't have an alpha hydrogen, which means there'd be no confusion as to what happens in the first step. You see, if this doesn't have an alpha hydrogen, then the alpha hydrogen can't be removed. So there's no real confusion here about which one has the alpha hydrogen gone on it if we're talking about a cross Claisen. But this one here is not a cross Claisen. Let's go back to where I was here. Hang on. As you can see here, this is just it looks like a single thing, but there's really going to be 2 of them reacting together to give the final product here. So when we're looking at a reaction like this one, it's sometimes helpful to draw out the entire thing here. And as I said, we know that we're going to be reacting 2 equivalents of this same thing, even though it doesn't say the 2 out the front. We know that due to the nature of the reaction, the actual reagents that we're talking about here, that we are going to be reacting 2 together. The pattern, or the general pattern for this reaction, I'm not going to go through the mechanism. If you want to go through the mechanism, I recommend that you watch the video. We'll talk about that in a bit. But what happens here is we lose this, and these carbons join together like this, and that will give you that'll end up giving you that final product here, which will end up looking like this. I know it looks complicated, but if you just join them together the way that I'm showing you here, then it becomes a whole lot easier, I think. Does anybody have any questions about this one? Again, I cannot emphasize enough the importance of watching all the videos for these reactions. It makes things so much easier once you understand how to do them. Okay. So no other questions about that, hey?
No. Which one shows the stereochemistry that you have to, is that the cross Claisen?
No, actually the Claisen doesn't have any stereochemistry at all associated with it. It's only the aldol reaction that has that map.
Oh, okay. Okay.
The one that forms a double bond as a product. We will get to one of those in a bit, I'm sure. Yeah. Any other questions about the Claisen condensation? I'll show you an example of a cross Claisen, because on the test you won't get both. You'll get one or the other, but I'll show you a cross Claisen as well, just for kicks. So what I'll do is I'll do the same, pretty much the same reactant here. And I'll react it with, say, this ester. And you'll notice that at this point where I've got the arrow, there are no hydrogens. And that's the important point. That's what I mean by no alpha hydrogens. And that's really important when we're talking about a Claisen, cross Claisen, I should say. So what's going to happen here is that we're going to lose the hydrogen off the one that it's possible to lose the hydrogen from. We'll lose the OMe off here, and these guys will join together, just like we did before. But there's no confusion, because we know that the one that loses the hydrogen is the one that has the alpha hydrogen. The other one, obviously, is going to lose the other part, the OMe part. Whoops. There we go. See, it's not too difficult. So that would be the cross Claisen right there. I'm really hoping that you all aren't completely lost and I'm not speaking all above your heads here. But if I am, and you need some clarification, please unmute yourself and ask a question. So I'm here for you guys. Does anybody have any questions? Okay. Let's take a look at the next one. The next one is the alkylation of an asymmetric ketone. Now, the reason I'm saying it's asymmetric is because you can see that there's a group on this side but not on the other. And due to the kind of reagents we're talking about, there's going to be two possibilities that we could come up with for this when we're talking about an asymmetric ketone and we're talking about adding an alkyl group to it. The product in this case could look like this, which means that you've got the 3-carbon alkyl chain joining to this side, or we have another possibility where the 3-carbon chain could be joining to this side like this. And that means that, you can see that on this side, it's what I would call the unhindered side. And this side, I'd call it the busy side, if you will. And which way it goes is dependent on these reagents. Understand why? Because it makes remembering the reaction a whole lot easier. Let's see if we can find it here. There we go. So the there's the two reactions there, the two possibilities. One that involves what I'm calling thermodynamic nucleophilic addition, and another one involving kinetic nucleophilic addition. So as you can see, the thermodynamic one, it goes a certain way because of the stability we get from a certain intermediate, which is the negative sign here, which forms a double bond that is more substituted. Whereas with the kinetic one, which happens with LDA at minus 78 degrees, that one.
I have a question.
Yeah.
On that, okay,
on that one.
So on the summer 2017 test for that question, it shows the. I'll
have to. Sorry, yeah. Let me pull it up. See, you said summer 2017.
Yes.
Okay. So I'll just bring it up, but then I'll close it so we don't have too much confusion. All right, let's see if we can find it.
The first one.
Oh, the first one?
Mm.
That's, yeah, okay. So what's your question about that, Matt?
Why doesn't that attach to the other side, the other alpha carbon?
Well, the answer, I haven't looked at the answer to that, but it should. Let's see what the answer should be for that. Let me pull this over here. All right. So from what I was just saying, this is a thermodynamic one. So I would expect this to be on the same side. Sorry about the shape there. That's what I would have come up with. So you said for this one, it should be the same. Did I check the wrong one? It's possible I did. But this should be the answer. Sorry if I didn't check that.
Okay.
Right. Because they should be on the same side. Now, if it was LDA and minus 78 degrees, it would be on the opposite side.
Okay.
Yeah, sorry about that, Matt. You're right. Okay. I'll close this other one down for now. All right. Did anybody have any other questions about that? Again, watch the video for it. All right, this one here is 1.4/1.2 addition. Let me show you where that is in the reactions here. Here we go. So there's alpha, these are called alpha beta unsaturated carbonyl compounds. Alpha being this position here next to C double bond O, beta being this position here. Unsaturated meaning we have a double bond in this position. And there's two different modes of addition that we can look at here. One involves organolithiums and one involves organocopper lithiums. As I showed you in the what to expect for test 4, you'll get one of these. Now the organolithiums will go 1,2, which means that the reaction will be on this carbon here. The ones with the copper in them, copper lithiums, will attack at carbon 4 here. Now, a question I've often been getting here is the direction of these arrows here. In this step where we're forming the ketone back from the enol, this is a C double bond C with no H on it. The direction of these arrows is not important. I mean, they have to be going opposite directions, but they don't have to be specifically the directions I have here. So I think in one of my videos, I've got the arrows going the opposite direction. That's caused a little bit of confusion for people, but it really doesn't matter which way that goes. All right, so going back to the question that we had here, you can see that because it's an organolithium, there's no copper there, we know it's going to be a 1,2 addition, which means it's going to be a direct attack on the carbonyl at this point, as opposed to this point over here. So let's take a look at what that product would look like. So it's going to be an alcohol, and the product will look, well, I'll just draw out the thing here. So the double bond here will remain unaffected. And then this whole thing here that I'm circling is what joins on. I know it's kind of different shape, but I think it's right. Yeah, that's right. But it joins on to that specific carbon there. The mechanism is what I've got going on over here. You can see how that goes. How the negative comes in, attacks the C double bond O, then the negative takes the H plus, and you'll notice the double bond here remains intact. Does anybody have any questions? Okay. This next reaction is called an Syllable Condensation. You'll definitely get one of these on the test, and it's characterized by the joining together of these two ester groupings. And the product for this one is going to look a lot like this. It's going, well, I'll just draw it out here so I can number things. Now, what makes this an Asymmetric condensation is the reagents, which is sodium, metallic sodium, and H plus as a second step. There's a similar reaction called a Dieckmann condensation, which starts off with a similar reagent here, reactant, but it has different things on the arrow. Now, we'll see an example of that. I shall show you an example of a Dieckmann condensation here, just so you can compare them, because sometimes people get mixed up between the two. This business here, this would be a Dieckmann condensation that you're seeing in the roadmap problem, which we'll go through a bit later on. But that's got a similar reagent or reactant at the beginning, but look at what's on the arrow. You've got NaOMe and methanol. That's different to what's going on here, which is the sodium metal. Now, the product is going to involve the joining of these two groupings, and what we end up with is this product here. Now, I'm going to have to change the shape of these things a little bit. So that's what the final product will look like. That's going to be based around the joining of those two ester groupings. And again, the story is told by the mechanism for that as to exactly why we get that product. Does anybody have any questions about the Asylum condensation? Okay, we talked about these next two during a Zoom session that I had previously a couple of weeks ago. I'll go over them again, just reiterate what you'll need to do as far as showing the different kinds of structures. I did record at least the first part of that session, which includes what I'm doing here. So you're more than welcome to go back and take a look at that. But I'll go through and show you how these are set up. So I would recommend I would recommend setting these up a certain way. I talked about it as being what I called a Pac-Man style, which means we've got the diene, which has these two double bonds on it here, joining with the dienophile, and what I meant by Pac-Man style is it's almost like these two double bonds are like jaws, and they're interacting with the double bond here on the dienophile, kind of almost like it's going to eat it up. The mechanism looks like this, and as I've talked about in the video for this, it doesn't matter what way those arrows are going. It does matter what's being joined together though, and the basis will always be this kind of setup. And we're always getting this six-membered ring somewhere in the structure. Now, the other thing that's important about this is, yeah, we're going to get that basic structure in the middle there that's based on the joining together of all those bonds. And there's that double bond there. And then we need to show the stereochemistry as dashes or wedges like this. So either both up or both down, and the reason for that is because these are cis here. So it has to be cis down here as well. So if you remember what I talked about with the double bonds, that's a cis double bond and that's a trans double bond. This one here is a cis double bond. They're both on the same side. Does anybody have any questions about that top one? So you do definitely need to show the stereochemistry, and you'll definitely get one of these that has what I call a 2D structure. That's that one. And then one like the one down below, which has a 3D structure or needs to be shown. And again, this was something I had gone through on that Zoom session that I had a couple of weeks ago. So going through this one here, again, we need to show the 3D structure. And I would encourage you to watch the videos and the Zoom session associated with that, if you are unfamiliar with what I'm talking about. So again, setting this up Pac-Man style. And possibly, if you want to, putting in those carbons at the ends of the diene and the ends of the dienophile, so you can more easily see what's been put together. It's usually helpful, I think, to draw a 2D diagram first before you draw the 3D. But you won't get any credit for the 2D diagram. I know that's going to upset you. Oh, well. And again, it's cis, so that's why I'm drawing this stereochemistry in here on the 2D. So you can see what's joined together there, where the double bond ends up. Does anybody have any questions about the 2D first? The way that's put together? Okay, with the 3D, I always encourage you to draw this shape first, which is emulative. Actually, I'll draw it in different colors here. Of the carbons that all join together here. All right. Yeah. And that's always going to be the way it's set up. All right, anybody got any questions so far? So then we can join the different bits and pieces to that. So we've got, these are the 2 carbons here, which I'll draw in. And these are the 2 carbons down here, which are these 2 here. And we'll look at what's attached to those first. And you've got that bridge there, which is this triangle business. And then those two groups attached there. Then over here, we're going to have that 5-membered ring, but it's going to be flat. It's in the same plane because that's a double bond there. And that's sp2 hybridization. And then this is going to be single bonds. So I'll push these downwards here. Try and draw it pretty. And that's what that would look like. They could be both up though as well. So either both up or both down, it doesn't really matter. But those have to definitely be pointing up or down. But it's important to understand the difference between this situation, which is planar, and this situation, which is not planar, where you're going to have ups and downs. So I'll draw it a little bit different. So the difference is that one of them has a double bond, one of them is a single bond. So the things are going to be different attached to them. All right, does anybody have any questions about that? It's probably the most difficult thing on the test, actually. It's what annoys most students. But you know, a lot of people are afraid of the question. Now they'll look at it and they'll say, "Oh gosh, I can never do that." But you'd be surprised. You'd be surprised. Does anybody have any questions about either of those that I'm looking at there? Well, nobody's saying nothing. So I've got to assume that you figured out what's going on. All right, moving on. Now this here at the top, this is an aldol condensation. More specifically, I'd call it a crossed aldol condensation. And again, it's a crossed aldol in the same way that the other one was a crossed Claisen. So let's go take a squiz at what that looks like. Here we go. All right, so this is the aldol, which involves 2 of the same thing, and those 2 things obviously have alpha hydrogens on them. And then the crossed aldol, you'll see that one has an alpha hydrogen, the other one doesn't. That's going to be the difference between them. The products are pretty similar actually, but the means that they come about are a little bit different, because in the case of the crossed aldol, the only thing that can be attacked in the first step is the one that has the alpha hydrogen. And the one that gets attacked by the negative charge is the one that doesn't have the alpha hydrogen. In the case of the regular aldol, you can see that it's really attacking another molecule of itself. So there's the difference there. Does anybody have any questions about what I mean by aldols versus crossed aldol? And again, I think the video does a pretty good job of explaining that. Let's go back to the test here. So you've got the ketone here that doesn't have any alpha hydrogens. And what I mean by that is there's no hydrogen attached here, no hydrogen attached here. So that's what makes it a crossed aldol. This is an aldehyde, and it does have an alpha hydrogen. It's right here. Now the way that these join together is actually kind of fun. I like the pattern associated with this kind of reaction. So we've got our compound here. It doesn't have the alpha hydrogens on it. And then we've got the aldehyde here, which I'm going to draw out a bit more completely. right? And what happens is you get these things joining together, that forms water, and then we get a CC double bond that forms. Now this isn't a mechanism, it's just a pattern. Now I'm not completed here yet, right? There's something else I'm going to add at the end. Sorry about that. Didn't mean to put that in there. Now I'm not done yet. Well, maybe I am. I don't know. We'll have to see in a second. But I need to know whether or not I'm going to have cis-trans stereochemistry. So in this video, I talk a lot about squigglies. I don't know if you've watched the squiggly video yet. And of course, the big question is, when do you put the squigglies in and when don't you put the squigglies in? Oh, it's a good question. All right. Well, I'll leave it open to the floor here. Anybody got any thoughts about whether I need squigglies or not for this one? Any thoughts? Ooh, squigglies. Well, okay, so do you need a bit more clarification about what I mean by squigglies? All right, well, let's talk about that a little bit then. So let's say we've got this situation here. These are representative of two possibilities that we can get for arrangement of things around a CC double bond. And the other way I can set this up is to express it, instead of drawing them both out the way I have here, is to express it like that, or like that. So you can put squigglies on one side or the other, but not both. And in that situation, yeah, if those are all different groups, yes, I would have to do that. But let's look at a situation where that wouldn't happen. So let's say we've got this kind of thing going on here. This situation wouldn't have squigglies because you've got two of the same thing there. If you switch them around, it's the same thing. So that's what you would do it. That's when you do it. You do it when you have different groups attached to both sides, both carbons here. Both have to have different, well, one of them, no, they both have to have different groups attached. Otherwise, you would have to put in the squigglies the way I've got them here. Does anybody have any questions? So looking at this one, I'll ask you again, does it need squigglies or not? I do see some people shaking their head no, which is good because it doesn't need squigglies. Does anybody have any questions? Oh, come on. People always have questions about squigglies. You're not going to tell me you all understand that. All right, let's do another example. I'll do an example of an aldol condensation with that same reagent that I have up the top there. And we'll see if this one needs squigglies or not. All right. I'm going to redraw this down here a bit more, make it a bit easier. All right. So the same pattern, and you can see they join together, and then we put in the groupings here. All right, that's a fun pattern. I like the Aldol pattern. Yeah, he's easy. Look at that. All right, squigglies or no squigglies? Any thoughts about that? Somebody want to say something?
Squigglies.
Yeah, squigglies. Squigglies will go in here. Where do we put them? It doesn't matter. You put them on the top or the bottom, but not both. All right, so let's put them on the top. There we go. Done. So that's just to represent the fact that we could have two possibilities. Either the hydrogen's on this side and this group's on this side, or it's switched. That's all the squigglies are saying. Now, if you don't like squigglies, some people have a religious aversion to them. I don't know. Maybe they do. What's the alternative? Draw out both. Draw out both. If you don't like squigglies, do this. I don't have a problem. But this is all you're saying. The squigglies are just telling a shorter story. There we go. So that's the same thing. That's equivalent. That's the same thing. If you want to do that, that's fine with me. All right, does anybody have any questions? No squiggly related questions at all out there? So Matt, you were asking earlier about stereochemistry. It's the aldol that needs to have the stereochemistry shown. The Claisen doesn't have any of that business going because it doesn't form a CC double bond.
Okay.
All right. Any other questions about that? All right. Well, next one there. The next one here is an enamine assisted nucleophilic addition. And this one, I'll never ask you to do the mechanism for it, but if you want to do the mechanism, you can get a bonus point for it. Most people usually don't because it's kind of complicated and annoying. Let's see if I can find him. There we go. So that's B, enamine assisted nucleophilic addition. I have a video about this as well. And it does the same thing as the one above, A, except it's under conditions that are a lot easier to access in most laboratories. The top one you have to do under completely dry conditions, which is really annoying. And the other one can be done under aqueous conditions, which makes it a lot more convenient. But that's what that reaction is there. Anybody have any questions about it? Well, let's look at what the product is. Very, very simple to do the product for this one, by the way. So the product is just going to be the ketone that we start with. And then since it's symmetric, it doesn't matter which side you put this on, but this is going to be a 3-carbon chain that plonks on either side of that, but it goes on the alpha carbon, the carbon next to the C double bond O. All right, any questions about that one?
Dr. Musgrave.
Yes.
Will it always be symmetric? No.
For that one, yes, absolutely. The only asymmetric ones that are similar to that are the ones like we dealt with previously, where you can have something on one side or the other, and it matters what the reagents are. For this one, it will always be symmetric. Okay, this one here, this one is a Novnagel condensation, which is really just a special kind of aldol condensation. So let me show you the setup with that. It's kind of like a crossed Claisen, but it's a bit more confusing than that because, well, hang on, I have something here that has alpha hydrogens on it. And how do I know which one is going to give up the alpha hydrogens? Well, it turns out that when you've got a setup like this, that's called a dicarbonyl setup here, and we talk about this a lot when we get onto the acetoacetic ester synthesis. But it turns out these hydrogens here in between the two C double bond O's are actually pretty darn acidic. They have a pK of 11. So just for the sake of comparison, the pK of this is about 15. If you think back to test 1 when we talked about pKa's, and what I said was the lower the pKa, the more acidic something is. So it's amazing to think that hydrogens on carbons can actually be even more acidic than, say, the hydrogen on the oxygen of, say, even an alcohol like that one there. Well, not just more acidic, 10,000 times more acidic, 10 to the 4th, the 15 minus 11, 10 to the 4th times more acidic. So it's pretty amazing. So it's almost like here, on the other one, let's talk about what the pK of these suckers is. The pK of, say, that or that there, pK would be about pKa 23, something like that. Huge, I mean, so much higher pKa. So 10 to the 8th times less acidic than even an alcohol. So if you've got a base, and that's what this situation is up here. This is basic conditions in the NaOMe here in the MEOH. I call that Naomi and Meo. Naomi and Meo makes it a little bit easier for me. So with Naomi and Meo, what happens is that there's no contest. It's going to take these hydrogens here and not these down here. So it's pretty easy. So go on.
Apologize for interrupting.
That's all right.
Normally, when I think of basic conditions, I think of negative charges and acidic with a positive, like H plus.
Mm-hmm.
So that's erroneous thinking.
Well, no, it's not erroneous thinking. It's just failure to recognize that NaOMe is Na plus OMe minus, and that the Na plus is really just a counter ion and is going to be a spectator. So the rest of it is what's negative.
On the structure itself, when you pull off a hydrogen off that double carbonyl group,
yes,
are you making it, because it has a negative charge at that point, are you making it a basic structure, like a basic ion?
Well, yeah, I suppose it would be, but it's really going to be nucleophilic, because it's going to, that negative charge then will attack the other C double bond O on the other structure. And that's from the mechanism though. That goes into the mechanism of it. So let me see if I'm going to try and pull this up here, the Nov-Nagel. There we go, here he is. So you can see in the first step, you've got the OMe minus that takes the hydrogen off there. And then in the next step, that negative charge comes in and attacks the C double bond O from the other portion. That's where the basicness of the mechanism comes into play. Is that okay, Coley?
Yes, it's really, so these are really basic conditions for this reaction to occur.
Yes.
But because the hydrogen's so easily removed, you're saying that that's kind of making that hydrogen acidic.
Yes, that's right. Well, more acidic than the other one.
Than the OMe?
No, more acidic than, hang on. Let me go back to where I was here.
And this may be beyond, like I might be getting too.
More acidic than these guys here, Coley. So what I'm saying is the OMe minus has a choice. The OMe minus has a choice, effectively. It could take a hydrogen off here where I've got the cursor, or the hydrogen off here. It chooses this hydrogen because it's more acidic. Now, the reason it's more acidic, that comes down to something else that we've talked about as well. And that has to do with the stability of this anion, because this anion can resonate with both of these C double bond O groups. That's why that hydrogen doesn't mind coming off, because it's forming something where that negative charge is stabilized by two oxygens. Now that's a bit more advanced, but you know, that's something that you can get from the video as well. So what I'll do is I'll put all this together now. So we've got our two structures here, and for you, all you have to be aware of is, well, which one's going to give up the hydrogens and which one is going to react with the double bond O. So we put them together. It's just like an aldol, just like we talked about. So that goes in there like that. Then you've got to decide, do we need squigglies or not? Does anybody have any thoughts about whether we'll need squigglies? Yes or no?
Squigglies, yes.
Yes, squigglies. We will need squigglies. The reason we know that is because we look at this group, are they different? Yes, they are. We look down here, is this grouping different to this grouping? And yes, they are. So we need squigglies. Doesn't matter which end we put them on, but we have to put them on one of the ends. I'll put them on the bottom. There we go. So that's what the product would look like for that. And you know, the only point of ambiguity is, oh gosh, where do I get the hydrogens from? The alpha hydrogens. You always take them from the one that has the setup with the two C double bond O's in that arrangement, because the hydrogens are so much more acidic than the hydrogens on the other one. Does anybody have any questions about that? The Novnagel? Again, I'd encourage you to look at the video for that too. All right. Any other questions? Now let's take a quiz at the next one. The next one is called a microreaction. And what characterizes a microreaction is it's going to be a 1,4 addition, very similar to what we looked at earlier, except that this negative charge here is always going to attack at this end of the 1,4 system and not down over here at the C double bond O. And this can be this can be a number of things. Let's take a look at the notes here for the microreaction. And you can see that the nucleophiles that we can use here are things where a negative charge is next to a C double bond O like this, or in between two C double bond O's, just like we did for the Novnagel, or even an amine group. And the product is always one where the nucleophile ends up joined to the end of the CC double bond at this point here where I've got the cursor. So when we're looking at an example like the one I'm showing you here, and again, I think showing the mechanism for this is also useful. I'm not going to show it here, but actually doing the mechanism is helpful. So the product is going to look like this. It's going to still have the C double bond O there, but then this is just going to be plonked on at this specific position, because that's where the CC double bond ended. But whatever had the negative charge, that's what joins on there, like that, and joins on at that specific point. Does anybody have any questions? So yeah, so that's a microreaction. I'll just write that down here. So you can look that up and you can watch the video associated with that as well. All right, does anybody have any questions? All right, well, let's look at number 2 here. Number 2 talks about a competition reaction. And the competition here is specifically between these two kinds of product distributions, you'll notice that they're flip-flopped. One's at minus 100 degrees, that's what I'm calling low temperature, and one's at 70 degrees, and that I'm calling a high temperature. The products are the same. You can see them here. There's no difference. But look at the product distributions. For the low temperature one, it's this one that's 80%, this one's 20, and here, this one's 20% and this one's 80. That's the difference between them. So what we're going to do here is go through this and explain why one is going to be favored over the other. Does anybody have any questions before I get started with this one so far? The kind of question you're expecting on the test is going to have this same core, this diene core that we're talking about. Everything, anything that you have, it's just going to look like that, but it's going to have stuff joined to it. All right, so let's go through. We'll look at the mechanism first on how we get both of these products, and then we'll talk about why we get one set of products over the other. So I am still recording, which is great. I like that. Okay, so the first thing is we've got HBr, which is going to split into H plus and Br minus because it's an acid. And then it will add to the double bond like that. And the plus here specifically will end up on this carbon here and not the other carbon that I'm pointing at here. The reason for that is because if it's got a choice of putting the plus here and the plus here, the plus will always go on the more substituted carbon. That is the carbon that has more carbons attached to it. The background for that, again, I talk about it in the video, but we talk about tertiary C pluses versus secondary C pluses versus primary ones. Something we went through when we did test one, we talked about the carbocation stability. But I want you to be able to see that the positive charge here is going to be more favorable than putting it on the end. Does anybody have any questions? Yes. Taylor.
Will it always be symmetric?
Yeah.
Okay, cool.
It will, but there's always going to be a difference between the sides where the positive charge goes.
Right.
To make it different. Otherwise,
okay.
You'd get there and you'd say, oh gosh, I don't know where the plus goes.
Right.
That's horrible.
Okay, thank you.
So the Br minus then can just go ahead and plonk straight on there. That gives one of the products. That gives the, well, I guess the first product that you see there in the top. And you'll notice the other double bond there is untouched. And there you go. That explains the creation of one of those products. So I'll call that one product A. Now the other one, the other product that we see here, I'm going to start off with this positive charge where it is. Instead of the Br minus going on there, what happens is it's actually a resonance situation. That's why I've got the double-headed arrow there. And you'll see that the positive charge ends up over here. The double bond now ends up in the middle. And we've got this kind of situation here. Hang on, let me make sure I got that right. There we go. And the Br minus then can jump on the end like that, or where the positive charge is. And that gives me my other product. Which looks like that. And I'm going to call that product B. Does anybody have any questions? So you got the two products here, but I'm calling A and B. Here and here, A and B. I'm going to have to remove these because I need this space to draw some other stuff here. So now what we can do is we can draw an energy diagram to describe or explain why we get one over the other here. Actually, I wonder if I can, I'll leave that up. I'll see if I can open a new. Yeah, that'll be better. This will help explain it a bit better if I can show them side by side. So I'm going to draw an energy diagram here. Energy on this axis, reaction pathway on this axis. The start will be the diene business. And HBr. So that'll be the starting energy. And then we need to, let me see, I'm actually going to pull up the, I'm actually going to pull up the key for this too. So you can see it in all its glory as well. So you see, you end up getting this energy diagram that looks like that. And it's a double peak situation like this. And specifically, you'll see that one peak is less than the other. That's important. Now, the reason for that is that it's the first step here that is actually fairly high energy, where we're forming this positive charge here. If the next step has an activation energy that's fairly small, see, it's that line I just drew in there. The activation energy for the first step is a lot higher because we're actually forming a positive charge. This one here is a lot lower because we're combining a negative with a positive, which is always going to be a very easy kind of process, low energy. So that's where the two steps come into play here. Does anybody have any questions so far? Now I'm going to say that this is the pathway for A, for product A. The one for B is going to be higher energy like that, but the product is going to be lower over here. So that gives B there. So A is the product of A is higher energy than the product of B, but you'll notice that the activation energy, and that's for A, is lower than the activation energy for B. All right, so let's talk about why that is. If you look at the carbocation here, that's a tertiary C+, and as we talked about, that is going to be more stable than this situation, which is a secondary C+. So the actual carbocations we're talking about will be here at this point. So let me put a little bit of, I'll call this A+ here. I'll call this one B+. So this is going to be, this will be A+ here, and this will be B+ here. All right, I'm going to stop here for a second. Does anybody have any questions about A+ and B+ and what the nature of them is? The important point I'm trying to get across here is that A+, because it's got 3 carbons attached to the C with the plus on it, is going to be more stable than B+, which has 2 carbons attached to the C with the plus. You can count them here, 1, 2, This one here, 1, 2, 3. I'll draw them in. C, C, and C. And for this one, C and C. So that has an effect on the stability of those carbocations, which also has an effect on these activation energies here. Now, if you look at the products themselves of A and B, what you'll notice is that, so let me write in a couple of notes here. So the A plus here, that's a tertiary C plus, and the B plus here is a secondary C plus. And then when you look at products A and B themselves, you'll notice that A has a less substituted double bond, and B has a more substituted double bond. All right, so let me explain what I mean by that. When you look at A and you count the C's directly connected to the double bond, you'll see that this has 3 C's connected to it. And in the case of B, we've got 1, 2, 3, 4 C's connected to the double bond. That makes it more substituted. If it's a more substituted double bond, it's going to be more stable, more carbons connected to it. So that's what we have so far. So the interplays between the stability of the carbocations and the stability of the final products. Does anybody have any questions so far? Coley, you look like you're about to ask a question.
I'm getting these probably mixed up with the SN1 and SN2 reactions. So like with an SN1, I think that was you could do like a tertiary or secondary. In SN2, you could do a primary, right?
No, yeah, I don't really want to talk about
Okay.
talk about SN1, SN2. All I really want to talk about is relative stability of the positive charges of A plus and B plus.
And the primary would be even higher?
Yeah, well, worse, yeah. Worse.
Worse than A?
Yeah.
Okay, that's what I was looking. Okay, I should have just asked that. Thank you.
All right, does anybody have any other questions about this so far? So we talk about two things here. We talk about a kinetic product and a thermodynamic product. So I call A the kinetic product. And the kinetic product is all about comparing the activation energies. And as you can see, the activation energy for A plus is lower than the activation energy for B plus because the stability of the cations is, well, A plus is lower than B plus, so the activation energies are lower. And that means that the EA will then, this will be favored at low temperatures. So think about what EA is. Activation energy is the energy required to get the reaction to go. And what I'm saying is, if you've got a choice, if it's got a choice between these two, it'll go with the lower one because the temperature's low, so it can only get over the first hump. It can't get over the other hump. Or it gets over the other hump to a much lesser extent than it does the first hump at low temperature. So that's what I mean by kinetic product. It depends all on the activation energy, and that's really the key. So A is the kinetic product. Now B is what I'm calling the thermodynamic product. I'll just write thermoproduct. And that's going to be the one that has the more stable product. And that's really the key there for thermodynamics. It's all about product. It's talking about what's going on here and here, whereas the kinetic product is talking about what's going on here and here. So thermodynamics is all about products. Kinetics is all about activation energy. And that's the simplest way I can explain it. And we can see that B is the thermodynamic product because it's more stable. That's the one that has the more substituted double bond. It's more stable because it's got a lower energy here. Does anybody have any questions? I know it looks really messy. It looks a little bit clearer actually when you look at the keys, but that's the basics of it. Also, I'd recommend you watch the video too. Go through the video. I explained it a bit more neatly there as well. Does anybody have any questions though about this? I just wanted to go through the very rough basics of it, just to make sure you understood the differences between the two.
So for the test, you want us to show the mechanism of both the kinetic and thermodynamic pathways, and then also the reaction grid?
Yeah, that's right. The reaction diagram, that's right. And then I think it also asks in the question to say which one's the thermodynamic, which one's the kinetic product as well. Okay, any other questions about number 2? Okay. Hopefully you've all seen the video, what to expect for test 4, where I outlined, hang on. Where I outlined what you were going to see for the mechanism question. But the mechanism question could be an aldol, crossed aldol, Claisen, or cross Claisen. This specific one is a crossed aldol. I'm not going to go through the mechanism here. I'd encourage you to look at the mechanisms yourself. Practice the ones that are on the old tests that I gave you, and I think you should be okay. But just make sure you know all of those different mechanisms. Again, crossed aldol, aldol, Claisen, cross Claisen. Does anybody have any specific questions they want to ask about number 3? Just incidentally, looking at the product for number 3, you can see why it doesn't have squigglies on it. And you can see here that this group and this group are the same, which is why there's no squigglies here. If there were squigglies, I'd put them in, but I haven't here because I don't. Is everybody okay with that? Anybody have any questions? All right. Number 4, actually, number 4 is not a bad question. It's people usually do pretty well with it. It's the malonic ester or acetoacetic ester synthesis. And what we're doing here is going to depend entirely on what we're starting with. If we're starting with something that's got an OH like we've got here, then we're going to be using the malonic ester synthesis. And if it's going to be a CH3 there instead of an OH, then we're going to start off with acetoacetic ester. So the two possibilities, for starting materials, are going to be as follows. That one's malonic. I'll just write malonic underneath it. The other one is acetoacetic ester, or AAE. And these have specific products. This one will lead to a product that looks like this. And this one will lead to a product that looks like this. But the steps, whoops. But the steps are going to be very similar for both. Not exactly the same, but pretty similar. So that's the first thing you need to do is say, well, what's the product look like? Oh, okay, it's got an OH. That means I'm going to start off with malonic ester. That'll be your starting point. Anybody got any questions so far? So had that not been an OH, if that was just a line, leading to just a point, then you'd be starting off with the other one. And you could get either. I mean, you could get either. All right, let's take a look at how this goes then. So we're starting off with malonic ester. And we're going to use Naomi and Mio. And then we're going to add to that, instead of H+, which would just make this negative and then put an H back on, which we don't want to do, we're going to add some kind of alkyl halide. And we've got to figure out, what's that alkyl halide going to look like? I'm going to see if I can squeeze it in down here. And we'll look at how we identify that. Those look like they're going to be the same. How kind of me. I don't know if you're going to, I don't know if I'm going to be that kind to you, but we'll see. These are the groupings here. So that's going to be the alkyl group that we'll add. And it's important that we put a halogen on this specific carbon here because that's the one that adds to that carbon. So it's going to look like this. And then I'll put a Br here. But you can put any halogen like Br, I, or Cl. You can go there. Doesn't matter which. Anybody have any questions so far? So what will that do? That'll give us this. I think this one's kind of fun, actually. I'm not going to say everybody finds it fun, but people don't mind it. So you can see that puts the alkyl group there. Anybody got any questions? So we've got this other alkyl group down here, which I'm going to put a square around like that. And it's going to turn out it's the same thing in this case. It won't always be the same though. I think it was an accident here. Happy accident for this crew, but like I said, I don't know if you'll be so lucky. Okay, so now we've got both of those groups attached down there. Does anybody have any questions?
I have a question about
Yeah.
So we'll be able to determine what we're starting with by looking at the product and seeing if it's OH, then we know it starts off with MEO, and if it's just a line, then it would just be OH.
No. If you're starting off with, if the product has OH here, then we will start off with malonic.
Mm-hmm.
If there's no OH, if it's just a line, then it starts with this, the AAE.
Okay. All right. Thank you.
You can see they're very similar. One has a methyl and one has an OMe here. That's the only difference between them. So once we've got those alkyl groups attached, then we have to hydrolyze the ester group, turn it into a carboxylic acid. And in this instance, both of those end up turning into carboxylic acid groups. Everything else just gets plonked on here as well. And then in the last step, I'll put in the delta, that means heat. And that will turn it into that product there that you see. I'm not going to rewrite the product, don't have room, but it's that product there. That's called decarboxylation. And what that will do is remove that CO2 group there and just leave whatever's left over. And that's how you'll end up getting that product. So the main thing that I'm trying to get at here is just how you identify what the alkyl groups are, because the only things that really change are the things I'm putting these arrows on here, that and that. That's what's going to change, and obviously how they attach to the central carbon there, but everything else is going to be the same regardless of what you're dealing with. Does anybody have any questions? So as I said, that one's usually one that people don't have a great deal of trouble with. People, they don't tell me it's fun, but I think deep down they don't want to admit it. All right, any other questions about number 4? Okay, now number 5, well, this isn't Hang on. Let me see if I can repaginate this a little bit. There we go. That looks a lot better. All right. Yeah, this is another one. It looks really nasty, but it's actually not that bad. All right. Okay, so it's a combination of what we just looked at, the acetoacetic acid synthesis, and the Dieckmann condensation, which we haven't looked at yet. The Dieckmann condensation is really just a cyclic Claisen condensation. And what I'll do is, I'm not going to go through the mechanism for any of this. I'll just show you how to draw the products, the easiest way to draw the products for that. Whoops, hold on. Okay. So we'll start off here with the reagent that we've got at the very beginning. I'm going to draw it out with the ester groups on it. So make sure you understand that those are the same thing that I've drawn there. Does anybody have any questions so far? So what I would encourage you to do then is to number this chain, number it from one end to the other. So start from 1, 2, 3, 4, 5. Nope, sorry, 6. There we go, 5 and then 6, and you skip one there. All right. Now the nature of a Dieckmann condensation, and I'll just put it down here. I'll draw one that's a bit longer. The nature, and I'll just put an R here just to make it so it's not symmetric. I'll just go ahead and number this. So it's a 9 carbon chain, and the joining is going to be from the alpha carbon of one to the C double bond O of the other. So that would be from 2 to 9. It's a possibility. The other possibility, because this is not symmetric, is to go from 8 to 1. So from the alpha carbon of one side to cyclize to the other C double bond O. And I would encourage you again to look at the Claisen mechanism and the Dieckmann condensation videos to make sure you understand why that is from a mechanistic standpoint. But I'm just telling you this from a let's get the ring together kind of standpoint. Does anybody have any questions so far? So applying that same logic, we can do 5 to 1, or we can do 2 to 6. So we're going to end up with two different products. That's going to be A and B. But the catch is at the present time, we don't know what's A and what's B. So we're just going to have to go ahead and write those products out and see what we end up with. So let's do the 5 to 1 product first. Now it's going to be, as you can suggest, a 5-membered ring. 1, 2, 3, 4, 5. I can see that. Just a tip, the ring size we get will always be 1 less. And you can always look at the product down here to get an idea of the ring size too. See, that's 5-membered ring. So we're expecting a 5-membered ring. I'm going to go ahead and number it. I'll number it 1 through 5 because that's the way it was joined. Now the 1 is what's going to be left with the C double bond O, and the 5 is still going to have this COOMe connected to it. That's carbon 6. So that's always going to be the pattern, is that whatever the alpha carbon joins to, the C double bond O stays a C double bond O, And then whatever else is attached to that alpha carbon, like number 5 there, is still going to be there. So that's going to be one of the products, at least initially. So I still need to plonk some things on here. This is why I numbered it. There's going to be an ethyl group at 3 and a methyl group at 4. All right, any questions? That's the 5-to-1 product. I hope I haven't lost anybody. Have I lost anybody?
No.
All right. Okay, let's draw the other one. It's going to be a 6-membered ring as well. This is the 2-to-6, and we're going to number this. So I'll let's see. So 6 is going to be that. So 6, 5, 4, 3, 2, and then the 1 is going to be hanging off that. And then on 3 we'll have ethyl, and 4 will have a methyl. So that will be the other. That'll be the other product there. I probably should have put that next to it. I probably will. Let's see if I can move it, or if it's going to be a real mess. Yeah. There we go. Again. Right. So those are the 2 products we have so far. Does anybody have any questions? So then we apply that acetoacetic acid synthesis thing that we just did on the previous problem to this one. And what you'll notice is that we still have this kind of same basic setup here. Is with the C double bond O and the C double bond O and this central carbon here where we can put alkyl groups, just like we did previously. So let's go ahead and stick the ethyl group on in between those 2. It has to be specifically at that location. If people make a mistake with this, it's by putting this group in the wrong place. That by not recognizing that it has to go here at this specific location. They might put it on carbon, what I've got labeled there as carbon 4 because it's, I don't know, or maybe over here on carbon 2 or something they might do it. I don't know. It has to go in between them though. And that would be, well, it's either going to be C or D. We do the same thing with this one. There we go. Does anybody have any questions about that? Where the ethyl group goes? Why put an ethyl group there or anything like that? Okay, the next step is the hydrolysis step, which just changes the ester group into a carboxylic acid group. Again, this is just what we did previously. So this just turns this into an OH. Everything else stays the same. And that's going to be E or F at this point. Does anybody have any questions? Then in the last step, we just remove the CO, that carboxylic acid group. That's what the heating does, decarboxylation. I'm sort of running out of room here. I'll see if I can squeeze it in though. And those are the 2 products we end up with at the end. I'll stop right here for a second. Does anybody have any questions at all so far about this process? Okay. So now we just a matter of matching up these letters. So I have to look at those 2 products and figure out which one matches the one I have, which is this one right here, but I'm pointing to. So anybody want to tell me which one it is, left or right? So look at both of these, see which one match. Yeah, it's a left one. And the way you can do that, look at the order. It goes C double bond O, ethyl, methyl, ethyl. This one goes C double bond O, ethyl, methyl, ethyl. So you can see that that's that one there, which means that by extrapolation of that, that's going to be E. That's going to be D. That means that this here is going to be A, which makes this B, which makes this C, which makes this F, and that makes that G. And that's it. So this one is, again, one that people don't mind either. It's not too bad. It also gives you valuable clues. Let's say you forgot how to do the acetoacetic ester synthesis. You can see similar reagents here for the final steps, and that could help you if you forgot. Does anybody have any questions about number 5? You're all hunky-dory with it, huh? All right. Let's take a look at number 6. Again, number 6, he's not too bad either. I don't mind number 6. It's going to be a matter of looking at the products and being able to tell, well, where'd they come from? What kind of reaction did they come from? And the clue I can give you here is that when the setup looks like this, it's an aldol. And when the setup looks like this, it's a Claisen. So one thing you can do is, you know that you've got an aldol and a Claisen somewhere in question 1. That could help you. I mean, it could help you to determine what kind of reagents you're looking at. But if it's an aldol, then it came from ketones or aldehydes. And if it's a Claisen, then it came from an ester or esters. So what it's going to be a matter of is reversing those same patterns that I talked about when we looked at question 1. And actually, I don't think this is too bad. Let's take a look at the first one. As I said, it comes from an aldol. Let's go look at an aldol again, just for kicks. See if I can find it here. There we go. So the aldol here was the result of addition of 2 compounds that have C double bond O's in them as aldehydes or ketones. And when they join together, just to remind you what the product was of this one and how I put it together. So that joins together and we get this kind of product. Which didn't need squigglies, if you recall. I might have put too many carbons on that, but anyway, there we go. The point is we join them together by taking off those 2 hydrogens, taking off the oxygen, putting a double bond in there. All right, any questions so far? So what are we doing with this one? We're just reversing that. So let's take a look at what we've got here. We've got this. This is also a cross-Claisen, sorry, cross-aldol as well that we're dealing with, because we've got these 2 different things here. So what you'll do is just split that double bond there, and you know that one side's going to get a double bond O, and one side's going to get 2 hydrogens. All right, here's the $64,000 question. Can anybody tell me how you know which side gets the double bonded oxygen? Any thoughts?
Is it the one that doesn't already have the double bonded oxygen?
Yes, that's exactly right, Bonnie. Makes sense, doesn't it? There we go. And this one is the one that gets the hydrogens. There we go. Not too bad. I'll draw the hydrogens in just for kicks, but there we go. So it's just reversing that. And then you're wondering, oh, okay, what reagents do I use? Oh gosh, I wonder how I could figure that out. Oh, let's go back to question 1. We'll find that same reaction. Oh, there it is, NaOH, H2O, and heat. Oh, I'll just use those same reagents down here. Yeah, so it's not too bad. Does anybody have any questions about that one? Anything at all? Okay. I'm going to erase that. We'll look at the next one. Let's look at, well, this one is, it's a Claisen type situation. Let's go take a look at a similar Claisen. There we go. This one up the top here. And I'll just remind you of how that went, the pattern for that. So the way this works is that one of these loses an alpha hydrogen, the other one loses an OMe, and they join together like that from one of the alpha hydrogens to the other C double bond O. This is similar to the way we put together the Dieckmann, by the way, for that roadmap. Same kind of deal. And the product there looks like this. And you can see this one here, this bond that I've kind of dotting in here, that's the new bond between the two that we talked about, the alpha carbon and the C double bond O from the other one. Does anybody have any questions so far? Now, another subtle point here, if you look at the reagents, it's NaOMe, MEOH, and it matches the grouping on the ester here, the OMe. Those always have to match, by the way. I would encourage you to watch the video to see why that is. I don't want to go into it here, but I can tell you that you'll get product mixtures if that's not the case. So that is going to influence what we do in this situation down here. So there's our product. We've got to figure out, well, where'd that come from? Oh, okay. Well, let's see what's going on with it. Sorry, it looks like I messed that up there. Let's do that again. There we go. There we go. So look at the join that we're talking about here. It's between this C double bond O and this middle carbon here between the two C double bond O's. So just the comparative bond that we joined would be there. That's important as well. So finding that join point is going to be important. It's always going to be between the two C double bond O's, but it's basically the alpha and beta carbon to the ester group. So the first and second carbon away from the ester grouping, alpha and beta. So if we reverse the process here, you can see that the group that gets the ester grouping will be the one that doesn't have the ester grouping, and the group that gets the hydrogen will be the one that has the ester grouping. So it'll look like this. I'll put the hydrogen one on first and just detach it. So there's your hydrogen right there. And the other one, he's the one who gets the ester grouping. But notice how I put the same ester grouping on there, and that matters. The same ester grouping as I had on the previous one. So you'll notice this is just a straight Claisen because they're both the same. Does anybody have any questions so far about how I tore that apart? All right, so the reagents then, it's going to be 1 NaO and that same ester grouping, and the same alcohol as well, OH, and then second step H+. That's a little bit tricky, right? So everything there has to match. So both ester groupings on the things you made, along with the alcohol and the NaO whatever group, they all have to be the same for that one. Just like they were up here when I did this example. See, Me, OMe, OMe, MEOH, all of that has to match. Same with this. Does anybody have any questions about number 6? Okay. Does anybody have any general questions about test 4? Hopefully you've all seen the video. I've put up what to expect for test 4. All right. Well, I guess we'll leave it there. If you need me, just give me send me an email, and I'll help out. A lot of people have been sending me stuff, and I've been helping them out. I'll talk to you on the phone or on Zoom if I need to. But I'm here for you.
Thank you,
Just let
Dr.
me know.
Mustard.
No worries. Talk to you all later.
Thank you, Dr. Mustard.
Thank you.